This slide is connected with first order responses and acts as an introduction. First, we're going to consider first order systems where there is no input to the system. So consider a system which can be modelled by a first order differential equation with constant coefficients. Without loss of generality, we can write such an equation in the time constant form that's given here. You can see we've got a t dy dt plus y of t equals k times u of t, and ordinarily y is the state of the system and u is considered as the input to the system. Now, what we want to do is look at the behaviour of y of t for positive values of t when the input u is 0, but for a non-zero initial condition. So that means y of 0 will not be equal to 0. And what we want to focus on is how does the behaviour of y of t change as we change the coefficient t and the initial condition y of 0. Now, the time constant form is representative, and what we want to show first of all is that this is always a form that you can get to. So let's consider a more general representation of a first order system. Here it is. You can see I've written a dy dt plus byt equals c u of t, and what we want to show is that from this general form, which has got three parameters a, b and c, you can always get to the time constant form. Hopefully this is obvious to most viewers. What I'm going to do is divide every term in the equation by b. So you'll see here on the left I've now got a over b times dy dt. I've then got plus 1 times y of t, because b over b is 1, and then I've got c over b times u of t. And you'll notice this is now in time constant form, where capital T is a over b and capital K is c over b. So what we've shown there very simply is for an arbitrary first order form you can always move it into time constant form, and we're going to assume that you have done that for all the examples in this set of videos. So next, let's look at a first order model where you have got no input on the right hand side. So you'll see the right hand side has now become 0. So I've got t dx dt plus x equals 0. And what we want to recognise is the solution to this differential equation is given as x of t equals x of 0 times e to the minus t over capital T, where little t is time. Now, if you'd like to prove this, probably the easiest way is by substitution. Simply substitute this solution for x of t into the original differential equation, and you will prove very quickly that it satisfies the differential equation and therefore is a valid solution. If you want to prove it's the only valid solution, I suggest you look at some maths lectures, because that's beyond the remit of this video. Now, we could also verify the solution using Laplace. So what we've done here is solved this differential equation using Laplace method. So there's the original differential equation, you can see it, t dx dt plus x equals 0. I'm then going to define the Laplace of x of t as capital X of s, and people will probably recognise therefore that Laplace of dx dt is given here as s times x of s minus x of 0. So if I put those things together, then what I end up with is this solution here. Okay, that st plus 1 times x of s minus capital T x of 0 equals 0. If I rearrange this, which I've done at the bottom, you'll end up with this solution here. Capital X of s equals t x of 0 over st plus 1, and I can then rearrange that into the form x of 0 over s plus 1 over t, which is a standard form from the Laplace table, and therefore the solution follows. Now, let's have a look at how these responses look on a graph. We know what the response is. There it is, x of 0 times e to the minus t over capital T. But what does this look like when we sketch it? So what I'm going to do is substitute in some key values of t. So here we go, time equals capital T. And if I do that, then time over capital T becomes 1. And I'm going to substitute that into the equation above, x of 0 e to the minus t over t. And hopefully you'll see that I therefore get x of t equals x of 0 e to the minus 1. E to the minus 1 I can compute with my calculator, there it is, so I get 0.37 x of 0. Now that 0.37 is going to be quite important, and if I write this again, so you notice, we're basically saying e to the minus 1 equals 0.37 or approximate, and that's a key value to remember. What happens then if I substitute in t equals 2, capital T? Well, I hope it's no surprise to you that therefore time over capital T becomes 2, and therefore x of t becomes x of 0 e to the minus 2, and that's roughly 0.14 x of 0. What now if I put in t equals 3, capital T? Then you won't be surprised, I get x of t equals x of 0 e to the minus 3, which is roughly 0.05 x of 0. And finally, if I put in t equals 4, capital T, I'm going to end up with x of 0 e to the minus 4, or roughly 0.02 x of 0. Please note that all these numbers here on the right hand side are done to 2 decimal places. There is no point really doing them any more accurately, especially when you're only sketching. Now, what's the key observation here? The responses for a first order system are invariant if you use a timescale denoted in multiples of capital T. Okay? So you can see after capital T seconds I've always got 37% of x of 0. After 2 capital T seconds I've got 14% of x of 0. 3 capital T seconds I've got 5% of x of 0, and so on. So as long as I do the horizontal axis as multiples of capital T, then the graph is always the same. So we'll do an illustration here. Here we go. And you'll notice on the bottom axis here I've used a timescale written in terms of capital T, and that's a trick that you'll get familiar with. And so you'll notice after capital T seconds, if we start with 0 seconds, we've got x of 0. After capital T seconds we've got 37% of x of 0. After 2 capital T seconds I've got 14% of x of 0. After 3 capital T seconds I've got 5% of x of 0. So you'll notice this graph doesn't actually say what is capital T, it says whatever capital T you give me, this graph is true. So the shape of the graph is invariant if you choose the horizontal axis as capital T. Now, another key observation that you'll get used to, that we will use quite often, is you get to within 5% of the steady state value after 3 capital T seconds. And it's quite common to use 5% as an indication of I'm almost there. So that's the settling time. So some hints for sketching. So we've said now the response is invariant in terms of a timescale marked with multiples of capital T. So all we need to do is mark the time axis as 0, capital T, 2t, 3t, 4t, and so on, and then the actual graph becomes straightforward. The coordinate pairs that you'll need to remember will be time 0, x of 0, time capital T, 37% x of 0, time 2 capital T, 14% x of 0, time 3 capital T, 5% x of 0. So we modify the axis next by placing the actual values of time. So we basically cross out capital T and put the numeric value that we should have there. We'll show this with an example on the next slide. Okay. So here we go. We've got a system 6dx dt plus 4x equals 0, x of 0 equals 5. So how do we go about solving this? Well, step 1, put into time constant form. That's what we said was the first thing to do. So I'm going to write this here. I'm going to end up with 6 over 4 into dx dt plus x equals 0, and that tells me that t equals 1.5. Okay? Right, next, compute the values of x of t, x of 2t, and so on. So what I've got is x of t equals 0.37 times 5. Now I'm going to do this in my head, so I'll probably get it wrong, but I think that's about 1.85. X of 2t equals 0.14 times 5, which is going to be 0.7. X of 3t equals 0.05 times 5, which is 0.25. Okay, so hopefully you'll see how straightforward that is. And what I'll do now is I'll just clarify the times, because we'll need these. T equals 1.5, 2t equals 3, 3t equals 4.5. I'm going to be using those in a minute. So next, we'll put these values onto a sketch, which I'm going to do on the next slide, so it's nice and neat. So here we go. First, I'll draw an axis, and then I'll do exactly what I said. I'm going to mark the time axis first with just capital T, because that means that I can't get it wrong. And then I mark up here the initial condition, which was 5, and hopefully I'll get these roughly equispaced. It's only a sketch. So there we go. We've got x on the horizontal axis, x on the vertical axis, time on the horizontal axis. So what did we have? We had an initial condition of 5. Now at capital T we had 1.85, which is going to be about there. At capital 2T I think we had 0.7, which is about there, and capital 3T we had 0.25, which is about there. So you'll see I've got my points, and now I can do my sketch. It's not going to be perfect, but you'll get the idea. So there we go. There's my response. And finally, I can put the actual values of time down. And if you want to, you could even cross the original t. So put now down 1.5, 3, 4.5, 6. So, in summary, first-order systems with no inputs, so the input 0, are characterized by very simple observation. The response begins at the initial condition and finishes at 0. It follows a simple exponential curve, which is determined by the time constant capital T, and you can use multiples of t on the time axis, and then the curve is invariant. 100% at 0 seconds, 37% at t seconds, 14% at 2t seconds, 5% at 3t seconds.